All right, so let's get rolling here. All right, so it is 10:26 today. All righty, so it is 10:26, and this is Chem 11:10, Chapter 4, Day 3. And our objective is going to be able to determine both bond and molecular polarity. Alrighty, so now what we're going to do is we are going to kind of continue on where we left off the other day. And see what happens. Before I get carried away, we are going to lab on Wednesday. Okay, we're going to be in lab number 4 on Wednesday. Okay, so come to class ready to go. One thing I will say is we're going to be using Bunsen burners. Okay, so try to avoid long baggy shirts and stuff, so your sleeve doesn't, you know what I mean, you don't accidentally catch your sleeve on fire. I would prefer, short sleeve, things like that, but, just to understand that we are going to be we're going to be using Bunsen burners, so you'll want to be careful on that. Okay, all right, now I've been asked this question a lot, okay, and it's about electronegativity. Okay, electronegativity. I forgot the IV in there, didn't I? Now, what they do, okay, and this comes off of this chart, and it's a whole trend thing, just like all the other values we've looked at, and there's this chart right here, right? Ooh, that's ugly. There we go. All right, so what you need to understand is this. Is fluorine has the highest electronegativity. Okay, what that means is that in any bond that fluorine is sharing electrons with, okay, fluorine is stronger, which means it's going to do what to those electrons? Well, it's just going to hold them a little bit closer, okay, and that has an electronegativity of 4. Anything else it's bonded to, the fluorine is going to be stronger than, because it has the highest electronegativity. Now, you aren't going to have this chart on your test, and I wouldn't even write these down because there is a question on the test. Okay, and it gives you like 7 electronegativities as part of the question. Okay, so what I would do is if you come across a question that asks you about bond polarity, I'd put a little flag on it. Okay, and then once I got to the question that gives me all the electronegativities, I would just write them down, and then I would go back and do what? Answer that question. That way you don't have to dedicate a bunch of space on your 3x5 to something that they're going to give you on the test. Does that make sense? That's what I would do. Okay, because once you get to that question, if you get to that question early, it makes it nice. Because then you just got it for the rest of the test. And you'll know it the minute you say it. You go, oh, that's the question Mr. Denton's talking about. Because it gives you like 7 of them. And then they're the 7 they use on the test. So I would just write them down on my scratch paper and then go through and go back and answer them or use them for the rest of the test. Does that make sense? Okay? And then that way you don't have to dedicate any of your 3x5. Now what they do is, well, let me just show you right here. Okay? This is a little chart. This is on page 126, and it tells you what kind of bond you have. We're going to deal with 3 main kinds of bonds right now. Okay, you've got nonpolar covalent, you've got polar covalent, and you have ionic. And they fall into this range. Okay? So what that means is this. Is if I subtract your electronegativities, Subtract your electronegativities and this. If it is from 0 to 0.4. Now it says less than 0.5, but whatever. If it is 0.5, it doesn't count here. If it is from 0 to 0.4, this is considered non-polar covalent. But I'm going to be honest, that's not technically true. Okay? No matter what, if there's a difference in number, they are still going to be slightly what? Slightly polar no matter what. But they consider them, if they're in that range, they're going to be non-polar covalent. Okay? And if they are from 0.5 to 1.9, they are polar covalent. Okay, and then if they are greater than 1.9, which really means I've got to be what here? If we're only going by a tenth, what does it have to be here? Doesn't have to be a 2.0, right? Then it is going to be ionic. Okay? So what they'll do is they'll say, okay, let's look at, I don't know, let's just look at the FN bond. Let's look at that. Let's figure out what it is. Okay? Well, if you go back to that little chart, that chart tells me that F is a 4. Okay, and it's the highest. It's a 4. So I know N's got to be what? Less than that, right? So N is a 3.0. Okay, that's a difference of 1.0. Well, I just go to my chart. Well, that tells me that is going to be polar covalent. Okay? Now, what that means is that means that if I've got these two electrons, let's say I've got those two represent two bonding electrons, right? Those electrons are just going to hang out over here way more than they hang out over there. Okay? It's important we understand that, because what that does is that makes his bond now polar. They're going to introduce a couple of things here. One is this little symbol. Okay, this means slightly. That means that end of whatever that is, if this is part of a molecule or whatever, is going to be slightly negative. Well, by default, what does that do to this end? It makes it slightly positive. Okay? And that then is going to contribute to the polarity of the molecule. So we're talking about two things here. They've got individual bond polarity, and then you've got molecular polarity. Okay, so here's a good example. Let's say I look at water. Okay, let's say I look at water, H2O. Anybody remember anything about water from the other day?
Yeah,
it's bent, right? It's bent. Okay, so I've got my O here. I've got an H there. I've got an H there. And then I'm going to consider these two lone pairs up here. Okay? Now, we talked about this the other day. It's going to look just like this. Okay? These two lone pairs up here. Now, obviously, this is not a what? What did I not draw here? The triangles, right? So this is not three-dimensional, but it still gives us the same information. Now, what you need to understand is this. Is I'm going to look at this bond right here, and I'm saying, well, what's O? O is a 3.5. O is a 3.5. Okay, H is a 2.1. 2.1 and a 2.1. Okay, so my difference is 3.5 minus 2.1 is 1.4, right? So clearly this is a what? This is a polar covalent bond, right? They are sharing them, they are just not sharing them equally. Now, what does that do to my O then? Anybody know? It makes it slightly negative. What does that do to each one of my H's? Makes them slightly positive, slightly positive. Okay, now, another thing they'll use is what? Did anybody do any of these questions on the homework? Notice what they'll write right here? Nobody? They'll draw an arrow on this bond, and it'll look like this. Okay? Now, the tip goes to the negative end, which makes it easy. I think it would be a negative thing to be on the pointy end of an arrow. I don't know. Some of you bow hunters might understand that. And the fletching end makes a what? Makes a positive symbol, right? So this is the positive end of my bond. This is the negative end of my bond. And they'll do that on both sides. Now, what else that happens here? Yeah, Miller.
So you don't add up all the electronegativity, so it's like you.
No, it's per bond.
Per bond.
Per bond. Nalder. Because it has a larger electronegativity than the H does. It's always biggest minus smallest. Okay? Now, the other thing water has going for it is it's got two sets of lone pairs, right? So if I look at this bent molecule right here, up here, where these lone pairs are, is going to be really what? Negative. I've got, in addition to that, I've got polar bonds, which means I'm even more negative. And so what they'll do is they'll look at this two ways. This is my bond polarity, and then they'll look at it as a molecular polarity, and they'll do this. Okay? Meaning that this is a what? It is a polar molecule. And what that means is that I've got one end that is negative, where the lone pairs are. The other end opposite that is going to be positive. And that is one of the things that gives water some of its unique properties. Okay, has anybody heard the phrase like dissolves like? Nobody? Wow. Okay, does anybody know one of water's nicknames? Nobody. It's called the universal solvent. Does anybody know what that means? It dissolves what? A lot of stuff. That's what it is. And the reason it dissolves a lot of things is because it is polar. And because the phrase like dissolves like, something that's polar will dissolve other things that are polar. It will not dissolve things that are non-polar, which is why there's two kinds of paints in this world. There is nobody? Well, yeah. Does anybody know what water-based paints are called? Called latex. And then there is acrylic, which is, anybody? Oil-based, which is why some paints you can clean up with water, and the other paints you have to clean up with either gasoline or paint thinner, some kind of solvent. Okay? So yeah, and it's all based upon the fact that the molecules are polar. So now what they're going to do is this. They're going to give you a molecule. They're simply going to say, is this polar?
Oh, that's on the last Learn Smart, isn't it?
One of them. I don't remember which one. But yeah. So this is what they're going to do. They're going to give you a molecule. And it doesn't matter what it is. Let's say I give you ammonium. NH4 positive. Okay? Now what I would do is I would go and I would draw NH4 positive. Okay, well, I would probably draw the three-dimensional for this one. Okay? So what do I got going on here?
I got a question.
Yeah.
So nitrogen only wants to form 3 bonds. So is it okay if it forms 4 with the hydrogen?
Okay, who remembers what I said about that? Usually. That trend, the 8 minus the valence, right, is not a guarantee, but it is an often thing. And I would use that as a guide, but in this case, it can. It's got 4 H's. It has to form that bond. Okay? So how many electrons are at my party? 9?
Oh, 10.
10?
10, because there's an extra positive.
There's an extra positive?
No, it's 8. What? Holy crap. No, it's, 8. Because, so nitrogen has 5.
Well, I've got 1 N at 5 for a total of 5, right?
So 4 heliums.
I got, 4 hydrogens at 1.
I need to go to bed.
5, 4. This is a positive, though. So I minus 1 electron for a total of 8 electrons, right?
We're there.
Now I know that N's going to go where?
Middle.
In the middle, right? Then I'm going to go 3D here. like that. I've got that, and I've got a positive, right? That's pretty much what we did there, correct?
Yeah.
Now, I'm going to look at my electronegativity numbers. Okay, N is a 3.0. H is a 2.1, which puts them at what? 0.9, which means they are polar covalent. Do we all follow that much?
How do you know the nitrogen?
What?
It's just the chart.
It's the chart.
Yeah, it's off that chart. You guys, it's going to do what? What did I explain? There's going to be a question on the test that gives you all those values. Flag them all till I get to that question. Write it down. Go back and answer them. That way you don't have to devote any of that space on your 3x5 to that, which I think is probably the smartest. Yeah.
So it's per bond, so even if it's nitrogen's bonded to a lot of things that are 2.1, the 2.1 doesn't add up. It's just like...
No, yeah, it's just each bond. So right now, if I was looking at this top bond right here, this N and this H,
Right.
okay, the N's a 3.0, the H is a 2.1,
Right.
which means this bond is going to be going that way, right?
Yeah, but then if you're worrying about a different bond to a hydrogen, you don't worry about
No,
anything.
no. So this bond is going to be going that way, that bond's going to be going that way, and that bond's going to be going that way.
And then I got one more question.
Yeah.
So on one of the Learn Smarts, it gave us a crazy complicated molecule that had like a big tree right here, big tree right here. They were both it was like ended with carbon at the middle and double bonded to oxygen, which was like at the very middle. How do you tell how do you tell polarity if it's like two different molecules bonded to it? It was weird. I can't really explain it. I'd have to go back.
Yeah, well, you'll have to pull that up.
Well,
Because most of the time they ask about just right here. What is the bond around this atom? And then none of that other stuff matters. I just look at what's attached to it.
yeah, no, it pulled up a crazy complex. Well, maybe not to you, but like to me, it was pretty
Yeah.
complicated. And then it was like,
Find it. We'll look at it.
Okay.
Okay? Now, each one of my bonds is polar, but is my molecule polar?
No, I don't think so. Because there's no lone pairs that makes one side more negative.
Okay, you're right. That's a dead giveaway, usually. If there's lone pairs on that central atom, it's probably going to be polar. All right, there's no lone pairs here, but think about it. Let's pretend I'm in space, and this is a tree stump. Okay, and I hook up 4 rocket ships to that tree stump. And those rocket ships all fly out in that direction. Is that tree stump going to move? Why not? Yeah, they're all pulling equally, but they're pulling against each other, right? Now this, what's the difference here? Instead of pulling away, they're all pushing in. Would that make a difference? No, because if they're all pushing in, they're all still going to do what to each other? They're still going to cancel each other out. So would this be a polar molecule? No, this is a non-polar molecule. Even though the bonds are polar, the net molecule is non-polar.
Well, but it's only non-polar because all the hydrogens have the same electronegativity.
Yeah.
So if you were to switch out one of the this would have...
Yeah, no, you're right. No, that could happen. So you're saying, let's say I made this a fluorine.
Yeah.
Yeah.
It would become polar.
Then it would be.
Yeah.
Because these would be pushing in and that'd be pulling out.
Right.
It's like you're on Trek, right? I got one guy pulling. I know someone knows what I'm talking about, right?
That was funny.
I got one guy pulling. We're going to be moving that direction, right?
Then you got the one guy chilling in the car eating all the
Well, yeah. I digress, but that was a funny reference.
No, that was
Okay.
Have you seen that movie? They made a movie.
Uh-uh.
That was hilarious.
No, but I could see how that could be humorous. Now, let's say I do, let's say I did this. Let's do NH3. Now, I'm pretty sure we've already drawn NH3, haven't we? Has this class done NH3? Anybody got NH3 in their notes? Have we?
Yeah,
We have?
Oh, yeah.
What does it look like?
Nitrogen in the middle. Oh, sorry.
And what?
with one lone pair.
One lone pair. So I'd probably put the one lone pair over there, right?
And
Then I got my H. I got my H. And I had my H like this, right? Okay, now, we already know, based upon the numbers, that each one of these are doing this, right? Got that, I got that, I got that, like that, right? So envision this. This is the exact example I was just talking about. Here's my tree stump. I got this lone pair up here, which is a bunch of negative, right? So it's going to be basically pulling negative up here. Each one of these are doing what? They're pushing. Their net effect is going to push that up, right? I've already got that lone pair that's negative there. So where would my arrow go? It'd go towards the lone pair, right? So in this, it would go straight up through the middle. I'd have my arrow point up here. I'd have my positive end down here. For this one, it would kind of go like that. And this would be a polar molecule, which is why ammonia dissolves in water. Water's polar, ammonia's polar. They will mix. Okay? And that's what they're going to look at. So again, make sure that you, when you get to that question, because you're all going to get it at a different time, that I write it down. So it gives you like 7 of them. Yes?
On the test, so they can have the molecules drawn. Do you like that?
Okay, so they will not. They're all good because it's really hard to do a three-dimensional in that test generator. So they're probably going to be mainly two. You're just going to have to be able to mentally say, okay, what do I got going here? So what this would probably look like is this. They would probably actually just do this. They would probably just do this. There's a lot of questions on the test that I know that they say, hey, where do the lone pairs go? Well, you're going to have to know there's going to be 2 lone pairs right there, right? Say that again.
Would the answer be like 2 lone pairs?
Yeah, that would be, well, it'd be a lone pair on nitrogen. Exactly, yeah. Again, remember that each one of these are multiple choice, right? So when in doubt, just read through every answer and put them where they go and see if it works. You know, and that's where you get into, they do have a couple of ugly molecules on the test. But most of that's there just to screw you up. It'll say, you know, given this ugly molecule, what's the bond angle right here? Now I just got to focus on it. What's around it? I got 3 things around it. No lone pairs. It's got to be trigonal planar. You know what I'm saying? And once you've seen a few of them, it's going to be, oh, there's 4 things around it, no lone pairs. It's got to be tetrahedral. You know, there's 4 things around it, 1 lone pair. It's got to be trigonal pyramidal. You know, it makes it pretty easy. And if you go back to that chart I showed you, that, you know, because I know you all read the textbook so much that, you know, you got that 5 chart down, you're going to have 7 questions just like that, easy.
Only gives you examples too.
Yeah. Okay. Alrighty. So polarity, polar bond trends. Now, one thing I did, and I don't remember if it was this class, but somebody asked me this question. The farther apart they are, the more polar they get. You get opposite sides, then they become ionic. But we already knew that. So like, if I look at this chart right here, understand that these are the metalloids, which means they surround the what? Remember what the metalloids did? They're around the what on the periodic table?
Oh, the steps.
The steps, right? Which separates the metals from the non-metals, right? So understand that no matter what, that if I've got something from the right side of the steps and something from the left side of the steps, it really doesn't matter what that value is. It's going to be what? It's going to be ionic. Do you know what I'm saying? Based upon what we know about a metal bonded to a non-metal. Okay? But it's when I get my 2 non-metals together that then I've got to say, okay, what are the values? Again, they're going to give you them in one of the questions on the test. Okay? So make sure I understand that. Now, let's say I did this. Let's say I went with checking my notes. Okay, let's say I did this. Let's say I've got C, Double bond OH. Let's say I've got this molecule. This was CH2O. I believe we drew this already. Does somebody have this in their notes? I think we did this one day, maybe last time. Now, there's two kinds of questions it can ask me here. It can ask me about bond polarity, or it can ask me about what? Molecular polarity. Okay, so let's do them both. So, is the CH bond polar? Well, I know that carbon is, we already know hydrogen. What's hydrogen? Hydrogen is a 2.1, right? So, you get a 2.1 and a 2.1. Carbon is a 2.5. Carbon is a 2.5, right? Oxygen is a 3.5, correct? Okay, so they would consider these non-polar covalent, right? But no matter what, those numbers are different, right? So what they do is they just make a smaller arrow. The bigger the difference, the bigger the arrow, right? So these would have short little arrows on them. Okay? Now, this difference is 1. So it is polar covalent, and its arrow would be a little bit what? A little bit bigger, right? I got that. Now I want to look at the entire molecule. Well, what shape is this? Yeah, 3 things around me, no lone pairs. Trigonal planar, right? So I'm all in the same plane. I got these pushing that way. I got that pulling this way. Is that going to be a polar molecule? Definitely, and it would basically go right down through the middle, just like that. Yes?
So for determining electronegativity, do the lone pairs around the outside atoms matter?
They do a little bit. In this case, they do, because what this means is that I've not only got a polar bond, I've got lone pairs as well. And lone pairs always contribute to that end being negative.
Because I know with the shape and arrangement, you said it only matters.
Yeah, then it's a central atom. But this, yeah. The only time that doesn't matter is, let's say I had, let's say I did this one. Let's say I did CCl4, right? So it's going to look like this. Okay, that's carbon tetrachloride. This is carbon tetrachloride. Now, carbon is a 2.5. Chlorine is a 3.0. Right? So what would I have going on here? The bonds are polar, so I'd have an arrow going which direction? Yeah, out on each one of these, right? And there would all be the same value, so all the arrows would be the same length, right? Now, what if I wanted to assign little partial symbols here? What would happen? Chlorine slightly negative, slightly negative, slightly negative, slightly negative, which means my carbon's got to be slightly positive, right? Now, is this molecule polar? No. The molecule is non-polar because all those arrows are basically doing what to each other? Yeah, they're basically canceling each other out. Okay, that would be an exact analogy of like the spaceship one. All pulling in opposite directions are going to cancel each other out. Okay? Is that making any sense? Yeah? Should we try one? Yeah? Alrighty, so let's do... Let's do CH3Cl. CH3Cl. Let's go for 10 hands here. And what I want you to do is I want to see the drawing with the arrows, with the partials, and then I want to know both bond polarity and molecule polarity. Okay, so I'm going to give you a few minutes here, let you work on that, and I need 10 hands. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so we got plenty. All right, so who was 4? Who was 4? You were 5? So I know it was 1, 2. Drake, you were 3. I think you were 4. I'm pretty sure you were 4. Well, no shame in being wrong. Just tell me what you did.
So I had C in the middle,
Okay, so I got C,
and I had 3 hydrogen bonded to it.
3 H's, so like that. I probably would have done this, but it doesn't really matter. And then that's got to be where my Cl is, right?
Yeah.
Okay.
And then the little arrow things are going towards carbon on the H's.
So you're going this way, and this way, and this way. And we knew that from where? We had them from the other side of the paper, right? We had those numbers correct? Because carbon's at 2.5, H is at 2.1, right? Is that right?
Yes.
Okay, what's Cl? Oh, we got it right up there. It's a 3.0, right? So that arrow's going out, right? Probably, what's one problem with this so far? Yeah, I would probably make sure I had those lone pairs out here, like that. Oh, okay, okay, good job.
And then I just said it was non-polar.
Say it's non-polar. Anybody agree with that? I would say it's polar because think of this. I've got this arrow going out. Small, but it's still going this way, right? These are all going in. Wouldn't my net effect be to move this way? If I was thinking about it that way. Now, is it way polar? No, but still I would say I would have a short arrow going there, and I would say it is polar.
I got a question.
Yeah.
So if you were doing the slightly negatives or the slightly positive for the molecule,
I actually wanted them, but yeah.
yeah. So which one would you put for carbon? Because I did those two, but carbon's slightly positive.
Okay,
It's
so,
a chlorine bond,
on
but
this
it's
end-
negative.
On this end, it would be slightly negative,
Yeah.
which makes sense then that on the other side then would be slightly positive.
So would you just write it just a different place?
Yep, I would write it in a different place.
Alright, sweet.
Yep,
Then I
and then
got
all these are going to be slightly positive, slightly positive, slightly positive. And it makes it hard. And usually when they do this, they're going to ask these questions differently. They'll look at the bond individually, and then they'll look at they'll have a different question to look at the whole molecule because of that confusion.
Okay.
Okay? Does that make sense?
Yeah.
Okay, yo.
Would you put the slightly positive on the hydrogens even though it's not non-polar?
Okay, so it is non-polar based on the number, but who remembers what I said a few minutes ago?
It's still slightly.
No matter what, if their numbers are different, it's still going to be slightly, I would still put a little bit in there. Does that make sense? Because they call it non-polar, but there's still, as long as there's a difference, it is still going to be slightly there.
So is that why you put like the arrows too?
Yep, that's why I put the arrows too as well. Yes.
Is it the arrows that would label the bonds non-polar or polar?
It's just showing you
They would be considered non-polar covalent based on the number. But because they're different, there would still be a small arrow there. And that's what I was saying to Miller. They're going to ask these questions differently. They are. You know what I'm saying? They'll ask you a problem and say, okay, given this bond, what is it? Well, based upon the math, it's going to be what? Non-polar.
but it's still polar.
But when I go to draw this in a molecule, I would still need to account for that slight difference there. Do you all understand how they're going to be different questions? That's what you need to make sure you understand. Yes?
If you have two that have the same charge, like a carbon bond to a carbon, which way do you put the arrow?
You don't.
It's non-
No, but if it's carbon like this, and usually what you see is the 7 diatomics. If you go back a month, probably a month, we talked about the 7 diatomics. Anybody remember them? They're the ones they're usually going to do. They're going to do, like O2. Well, that's going to be O bonded to O. That is,
Can you move
sorry, that is what usually they refer to as purely covalent, which means they are shared 100% equal. Okay? And that, like I said, is typically reserved for the 7 diatomics, but there are some that are the same. Like if I take nitrogen and chlorine, they're both the same, right? So that would be a purely covalent bond. And in that example, there would be 0 what? There wouldn't be any arrows because they're equal. Does that make sense? So that's what you kind of got to watch for there. Okay? Yeah, there's a couple that are the same. And usually you'll notice that they're diagonal. It goes back to trends, right? So if I look at these two, notice that nitrogen is left of fluorine, chlorine is below fluorine. It's that whole trend thing, right? They're going to be equal, and you can see that in a few places, and that's how that works. Okay? All right, so the last thing we need to talk about today is we need to know how to name covalent compounds. All righty. You need to know the 10 Latin prefixes. Anybody know what I'm talking about? No?
Di, bi, tri.
So we got mono, di, tri. You know what 4 is? Already talked about it. Tetra, right? 5 is penta. These are geometric. Hexa. 7. Close. I heard it. Hepta. 8 is octa. Nona and deca. Okay? Deca. Now, so if I went, C2O5, what would that be called? Dicarbon. Is it pentaoxide? It's just pentoxide. Anytime these are a double vowel, you eliminate that. It's just pentoxide.
So if it was like 8, it would be octoxide?
It would be octoxide, yeah. Exactly. You just eliminate that double vowel. Okay? And it's like, here's a good one. It's like, let's say I went Bi3. Bi3. Right? Now, you never lead with mono. Ever. It's just never what's in front. Okay? So this would be what? It would be boron. I would never say monoboron. I would just say boron. And then this is going to be...
Boron triiodide.
Okay, now think about that.
Triodide.
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 Triodide. Not triiodide. Because then I got that double, you know what I'm saying? It's just boron triodide. Okay? Now, if mono's in the middle, then I use it. Like we should all be familiar with this, right? What's that? Carbon monoxide, right? Okay? If it's the mono's on the second one, you use it. You just never use mono in the first one. Okay? Carbon monoxide. Now, there are maybe 1 or 2 questions is all on this section of the test, which is really baffling to me. Because this is something they're going to use all year. They're going to just start naming things and expect you to know how to write it. You know what I'm saying? Like they'll write it out in words. So what I want to do is I just want to do a couple of these and make sure that we can get their names correctly. Okay? So let's say if I went with SIF4. Let's go raisey handy. Let's go 10 hands. SIF4. 1, 2. 3, 4, 5, 6, 7, 8, 9, 10. Alrighty, who was 7? What do you got for me? Silicon tetrafluoride. And do I need the A there? Yeah, because that's a consonant, not another vowel, right? Silicon tetrafluoride. Okay, let's go 15 hands. Here, I want to go... here we go. P2O5. There's no way you could have written that answer down that fast.
Oh, I thought we just needed to know it, not write it.
Oh, well, I would like it written down. I mean, because that would help. But I guess, yeah, I did not specify to have it written down, did I? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Alrighty, so who was 6? Down, what do you got for me? Diphosphorus, and you said what? Pentoxide, is he right? Yeah, just like that. Okay. Yeah, those are not too bad, and maybe that's why they only put a couple on the test, because like this stuff's too easy. Okay, but that's that. Okay. Alrighty, now, just a couple of things, and I am hoping someone wrote this down. Okay. Now, did anybody write down what I talked about between these two things? What one of the first things I talked about today was? After lab number 4 and before electronegativity. Does anybody have anything written down? Because I thought to myself, because I was using this paper, but I don't remember. I thought to myself, I probably should write that down. Okay, that makes sense, because then I went right into that, right? But there was something that seems like I talked about between those two things, and I can't remember what it is. And I thought, I'll remember that. I realized, hell, I don't even remember my own birthday, so that's probably not going to happen. And, yeah, it didn't happen. All right, well, hopefully I don't forget. All righty, so that is pretty much what I have. Remember, we are doing Lab 4 on Wednesday. Okay, and we're going to be working with Bunsen burners, so try not to wear baggy clothing. Okay, if you're a hoodie guy or gal, probably wear a short sleeve underneath it so you can take it off. Okay, just because I've seen more than one hoodie ruined on a Bunsen burner, and it sucks because then you get little white powder everywhere if I have to shoot you with the freaking fire extinguisher. Okay, so have your pre-lab must be done on Wednesday. What that does is that allows us to hopefully have one more day. So I'm thinking if we get the lab done, then we might have an extra day when we start fourth quarter to finish this up and then review and then take the test. So that's kind of my plans right now. So yeah, that's that. I'm not 100% sure about that because we'll see. Because I think I've got pretty much everything we need in as far as new material. I will go back through the test though and make sure. Yes?
So the homeworks will be counted on next course?
Yeah, so like everything is in except for the other lab. If you haven't done that lab yet, I'm taking that down this afternoon. So if you haven't done lab 3 yet, it's today or never. Do y'all understand that? Because that's going down today. Okay? And then, yeah, whatever's in is already in. I'm going to add lab 3, and that's it. That's your grade. We talked about this class being cumulative and all that other stuff. Okay. All righty. So time is yours. Use it wisely.